Here, let's talk about free body diagrams for 2D rigid body equilibrium. This is Jacob Greener. He was a student in statics a bunch of years ago. And I was walking by in Capital Commons one day and I was like, oh my gosh, look at Jacob. He's like riding a unicycle and slacklining. And the first thing that came to my mind, of course, was statics, right? Like, yeah, this is just all about statics. But actually, it wasn't like the force in the slack line or anything like that. What I was actually thinking about was how he had to learn how to ride a unicycle and slackline separately, right? Like, he didn't just like become really good at unicycle and then be like, oh, I'm just going to jump on a slackline one day, right? So he had to do both of those, but he had to master them separately. Well, the same thing for us. We have to be able to do our FBDs. We have to master the free body diagram, draw the correct free body diagram, and then we can start solving for it. So, right, so think about these as really two separate things, and we're gonna have two lectures. We're gonna have a lecture today that's really about mastering the FBD, and then on Friday, we'll talk about, okay, now solving this. We need to be able to draw the FBD and solve it. And then a couple weeks later, like a month later, Jacob sent me this picture, which is horrifying. It's super scary. They are tethered in, at least here though, but I thought this is just such a super cool picture with them slacklining on North Table Mountain here. This was actually this is what Jacob was doing during finals week. I think he was like using this as like he was de-stressing to do that. Okay, so our learning objectives here for 2D rigid body FBDs, we need to be able to draw the correct support reactions for all the stuff in this table 5.1, and we'll get there. Now remember, today we're not going to write down a lot of stuff. It's going to be more conceptual and just kind of seeing things in their physical presence and like, what does that mean and how can we use that? And then so once we can do that, we can draw free body diagrams that would allow us to solve for unknowns. Now in statics, it should be such that the entire problem can be solved without looking back at the original problem statement. So I know they don't do this in physics, but like if it's known, I better see it on the FBD. If it's unknown, you better have it labeled on the FBD. But like if there's a force of 500 pounds, like don't just label it F, label it 500 pounds. And then the other key parts of this are if we can determine the number of unknowns for any given FBD, that's really going to be super beneficial for us. We're going to talk about something called two-force and multi-force members, and then we'll talk about stability, instability, and indeterminacy as well today. Okay, so first, the FBD is a handwritten homework. So FBD number 14 is there is no mastering number 14, and so you're gonna go to handwritten homework number 6, and that's gonna have the PDF for all the problems that have that. Okay. Once you click on that, you're going to find these instructions. You're going to get the PDF, has all the problems. There's 15 possible points. So this handwritten homework is a little bit different. You're going to turn in the pictures for the problems on the attached. There's no handwritten homework 14 on mastering. Talked about the FBDs have to have all the known values and stuff like that on there. Same paper requirements as the other handwritten homework, but you only have to show the pictures. You don't need to write given, find solution for this one only. You can put more than one problem per page. Your work will be graded on format and content. So remember, this is 15 points here for these 5 problems. And I'll show you a picture of a couple of those. So our upcoming schedule is a little bit different. This on Sunday, the 28th here, so the last day of February, is when you have handwritten homework number 6 due, which is FBD number 14. No mastering due that day. So you have a handwritten homework on Friday, and then you have another one on Sunday. Okay, so just keep an eye on that. So it's actually really a pretty straightforward problem. It's, if you get it conceptually, it's going to be pretty easy. You don't have to solve for anything. The first two are, they ask us to draw an FBD of this. And so what we do is they say, oh, okay, well, I want to draw an FBD of this. The FBD of this basically looks like this. And I just make sure and include all my values on there. I got all my dimensions on there. And then I move on to the next one. And this first one does have parts A, B, and C. Make sure you draw a separate picture for parts A, B, and C. And then you move on to the next one, and you're going to draw an FBD of the wheelbarrow right there. And so then there's 5 of those problems. Okay, I would recommend starting it early so you can ask questions. Also remember there are recitations on Sunday. You can go to the Sunday recitations and get some help on this. So this might be a good Sunday to utilize those recitations. Maybe try to not overwhelm Emma too much, but certainly give her a run for her money. But maybe jump on it and work together or something. Okay. So back to Hoover Dam bypass bridge here. And so remember, when we're doing FBDs, right, we're separating this from the rest of the world. This one is only touching here and here. And so we got to remember to do that. And so, okay, so free body diagrams, it's our model. This is our model to predict the systems with forces, because what we get paid the big bucks for as engineers is we get paid the big bucks to predict how things are going to behave. And so let's write this down, okay? So we just, so what does it prevent? What does a support prevent? If it prevents translation, and what I mean by translation is just movement in any of the directions, right? So translation just means it's translating, it's moving in any of the directions. Well, we're going to use a force. If it prevents rotation, then we use a moment. All right, so preventing rotation means that it's preventing it from rotating. So basically, we're just asking, what does it allow and what does it prevent from happening? And we can just look at each of our supports and ask ourselves that question. Rather than trying to memorize these, and there's like 10 of them in this table 5.1 that we're going to look at. And so rather than trying to memorize this stuff, it's really just a matter of what does it prevent and what does it allow. So, for example, here's a pin support, okay? And a pin support, really all it is it's literally just, if I have a board here and this would be the same thing as doing this. If I have a board and it's got a hole in it, and then I say, oh, you know what? I'm going to stick a pin through here. And I stick a pin through there. And then we see that pin in this picture is fixed down to the rest of the world, right? Like this pin, or like the flanges that are attached to this pin, right? These triangle shaped things here, those are like attached to the rest of the world, aren't they? But then we see the pin right there. So there's this pin going through that. So if we were drawing an FBD of this rigid object right there, what is that preventing from happening? What is just the pin? And we don't consider the overall thing, right? The overall thing is obviously not moving, or hopefully it's not moving, right? Because this looks like part of a structure. This looks like some of the structure at DIA to me. I don't think it's at DIA, but it looks like it. So if I just did this and I was hanging on to this pin with my other hand, does this allow translation in the X direction? Does it allow translation in the Y direction? No, right? Does it allow it to rotate though? It allows it to rotate, doesn't it? Okay, so yeah, so we just say, okay, well, what does it prevent? It prevents translation in both the X and the Y direction, but it doesn't prevent rotation. So if we look at table 5.1, this is what it looks like in the book, is this picture right here. And it looks very similar, right? Like we got that triangle thing, that triangle shaped thing. They kind of have that little mark right there that looks like a pin, right? And it's just a pin going through there. And so they call it also a smooth pin or a hinge. It's the same thing. And then what do they show? Look, they take the pin off. So when we draw FBDs, remember we're separating from the rest of the world. So I would take the pin out like that. And what would I have? I would have just a rigid object. And I would have to draw this as an FX and an FY. Notice right here, right? There's no flange anymore. There's no flange. That's that triangle thing. And this is from table 5.1 of your textbook right there. So this is really what today is all about, is being able to see a picture like that in the textbook and know, oh, that's a pin, and I know it prevents translation from happening, so it prevents it moving in the x direction, it prevents it moving in the y direction, and so I know I'm going to have an fx and an fy force. Okay. How about, oh, here's another picture. In the textbook, you know, they say they're kind of breaking it down, right? They have the member, the pin, the leaves, and then they show it all combined from, and this would be like if you're looking down the side of this pin over here, right? So they've got the leaves, I guess, were what I called the flanges in that previous one, but we see the pin and the member, and then like it's an fx and it's an fy. Notice that this one is now horizontal, isn't it? So this member right here is now horizontal, but does it change fx and fy? No, fx and fy are still in the horizontal and vertical direction. So we're going to really break things into x and y components. Ooh, how about a roller support? This is a like a real roller. What do you think that prevents from happening? What do you think that allows to happen? Does it allow motion in the, it's basically like if you just take your water bottle, literally, so if you just take your water bottle here, and wouldn't it just allow movement? It's like a wheel. It is literally a wheel. So it doesn't allow movement in the x direction, but what does it prevent? It prevents it from moving in the y direction. And so we see our picture from the textbook just looks like a wheel in there right here, right? There's our wheel right there. And so what does we have? Well, we took the wheel off and we replaced it with a force only in the y direction. Okay, and then I see a question here. If the pin prevents translation, how do we have an x and a y force? So remember, we're replacing the physical thing with a force. So for example, if I pulled this, like if I had this right here and I pulled this roller away, what would happen? It's gonna fall, right? And so I say, okay, well, I'm replacing a physical object with a force. So I say, well, okay, I need a force right there that does the same thing that physical object was doing. And so I'm going to apply a force there to hold it up. And then this is our model that we can use to figure out, to predict what that force is going to equal in order to hold this bridge up. In this case is what that picture is showing right there. Okay, and so I see, let me see. And I see Brent said that it allows the material to expand and contract. Absolutely. And I want to point out one thing with that. Most bridges actually have a pin on one side and a roller on the other. That is so that as this board gets longer when it gets really hot outside, and as the bridge deck gets longer when it gets really hot outside, that it doesn't create extra stresses in that bridge. It allows it to get a little bit longer. Or when it gets really cold, it allows it to get a little bit shorter without creating additional stresses. We don't typically see a roller and a roller because that's a skateboard, right? We don't want skateboards. We want something to prevent translation in the X direction and not let it roll off there. Okay, and then let me see. So the FBD for both shows which direction forces are not translated in. So basically, if it's allowed to move in a direction, we don't want to put a force there, right? Because there shouldn't be a force. So like with this roller, you notice that there's no force in the X direction because there's nothing. This roller does not prevent translation in the X direction. Okay, does that make sense, Colin? Okay, and then allows translation. Yeah, and then it is also in an acceptable range, right? Yeah, it's not going to be infinite. It's not going to, right? But they figure out how much translation they need to allow And then I saw a question up here before, and I want to know if I answered it. Eilish, did I answer your question? Let me know if not. Okay, great. Okay, so there's our roller. Let's go into and actually let's look at all the table 5.1 connections. Now that we did two, a roller and a pin are like the two most common that we see in practice. Like when you're driving around town, you're going to see pins everywhere now. When in your rollers, you don't see them as much because they don't. A lot of rollers actually don't look like rollers. They're more friction rollers, or and we'll actually talk about that. They're like a contact kind of thing. Well, let's take a look at number one, a cable. Well, don't we know that for a cable, the line of action has to go along the cable? And also, don't we know for a cable that it can only resist tensile forces or pulling forces? And so what do we show? If we're drawing an FBD of the rigid object, we show a force pulling away from it because that's a pulling force. A weightless link, we're going to talk about this more. Right here, it's basically the same idea as a cable where the line of action is fixed, but they're saying it can go either in tension or it can go in compression or pushing on that rigid object. Here's our roller. And so we see this one, they're showing us a roller on an incline. Well, it's same idea though. What's it allowed to do? It's allowed to move up and down that incline. It's just not allowed to move perpendicular to the incline. So we see a force, and notice that that force is perpendicular to the incline. It doesn't matter what angle the rigid object is. It matters what angle the roller is, or what angle the plane where the roller is sitting on. That's what matters. That's what the theta there, right? They don't tell you the theta of that actual rigid object. And you can think about all the rigid objects they're showing in these, you can think about them as a board. Okay, or a piece of steel or whatever. A rocker. Again, they show a rocker on an incline, right? So very much like a roller, a rocker does the same thing. It allows this to move up and down along that plane there. So that's allowed to happen. There's nothing preventing that from happening. But it's not allowed to move into the plane. And so we see, again, perpendicular contact. I'll show you some real-world pictures of a rocker. Another very similar connection to a roller, a rocker, and then a smooth contact. So this is a frictionless contact. And again, what do we see? It's perpendicular to that contact. And notice that, right, it doesn't matter. It doesn't matter what angle our plane is at. It doesn't matter what angle our rigid object is at. All that matters is what angle our plane is at, right? So it's always going to be perpendicular to that plane for that force there. We can now kind of extend that knowledge into, say we had a roller or pin in a confined slot. So, well, that's allowed to move up and down in that slot, right? And now that it's confined, we can see the force can go in either direction. But when we were on a smooth contact, does that smooth contact ever prevent the rigid object from moving away from it? No, it's totally allowed for that to move away from our smooth contact, right? There's not glue holding it on there, but there is something preventing it from moving into the smooth contact, but moving away from it, no. So that's why we see only one case here and here, and that's pushing. This one, it can be either a pushing force or a pulling force there. And then I have a question, are ball bearings comparable to rollers? Yeah, but ball bearings typically allow like a shaft to rotate, right? So but same idea where they're just allowing things to move. But in this case, I think it's the ball bearings are more for like shafts, at least the ones I'm thinking of right now. The next one here we have is a pin connected to a collar on a smooth rod. And so if this is a smooth rod, well, it's allowed to move up and down. So that's allowed to happen, but it's not allowed to move perpendicular to that smooth rod in both directions. So we could draw it either way. And actually, when we have stuff like that you can draw in either direction, it doesn't matter what direction you draw it in. The math will tell us if it needs to go in the opposite direction that we drew it. And I don't even call it the wrong direction. It's not the wrong direction. It's just the opposite direction. Now, number 8 is our smooth pin. We've already talked about that. They do say in the textbook you can do it like this. Technically, yes, it's got 2 unknowns, just like an fx and an fy. But I don't want to have to solve for an angle. I don't want to have like some unknown phi to solve for. And so I would recommend not ever doing it that way, because it's the same number of unknowns. And then also, what do we usually do anyways? We break it into an x component and a y component when we solve for stuff or when we take moments. So doing it as a force and an angle, just not a great idea. Let me skip down to 10 right here. 10 is a fixed support. This fixed support is preventing, this is really our first one that prevents rotation, isn't it? This prevents this object from rotating, and it also prevents it from translating. So now we see a moment on there. And maybe this would clear things up too. I'm thinking these are reaction forces, right? These are not applied forces. These are like the reaction. So what this is saying is, like, if I had some force, if I was holding on to this rigid object like right there, and I prevented rotation from happening, well, I now have a reaction moment. And then if I'm holding it tight, do you think I could just grab it and pull it out of my hand? No, so I have an fx. And do you think I could just pull it up or down? No, I'm holding it up or down too. And so we see fx, fy, and a moment on that one. Now back up to number 10 here. So this is a fixed connection. So we see this is different than the other one, because this right here it's fixed. And so we see a moment on there, but it is allowed to translate in that direction. So it's allowed to do that. And so we have no force in that direction, but we do have a force perpendicular to that smooth rod. See a couple questions here in the chat. If the roller is connected to a point support, which one do we have to consider? A pin support. Oh, I see. I know what you're talking about. So this one, the way this looked up here is right here, right? That's like, it's got the pin that's connected right there. And then it's also got those rollers on there too, right? Well, what is this? Look at the overall connection. What is that overall connection allowing? So this overall connection allows it to move up and down, and it doesn't allow it to move in the perpendicular to the plane. So it's the roller would control in that one, and that's the one we would use. Good question. Okay, the 3 most common, and we talked about smooth pin, the roller, and the fixed support there. Those are the 3 most common in practice that we see around. A rocker support. Here's some pictures of rocker supports. Same idea as a roller and same idea as a smooth contact. And I just want to show these pictures to get a better idea, right? The rocker, again, it allows that translation in the horizontal direction for these pictures, right? So it's allowed really, and it's a finite amount of translation. But you can kind of see in this one where as it rocks, it kind of allows motion to move in that direction. But it prevents in this direction, so we would have a force that's acting on there. And then I have this picture down here. It's got all the names on it and stuff, but we don't need to know any of those names, but I thought it was kind of a cool picture there. Okay, here's a real-world example of a fixed support. This is an H pile that they drove into the ground. It's probably goes into the ground probably like 20 feet at least. So do you think if I went and pushed on this thing right here, do you think it would rotate? No, right? Do you think I could easily pull it out of the ground? No. Do you think I could push it in the ground? No. Do you think it would translate? No, right? So this is a fixed support right there. A fixed support really means that it is not going to translate, and it's also not going to rotate. And then just to remind everyone, if we look on this one right here, the way we show that fixed support is basically we just show it ending at a wall or something solid as the way that we show that it's a fixed support. And we typically write it in the problem statement too, right? The A is a fixed support and stuff like that. So we have these, I found this picture, actually there's an example of this in the Golden area too, where they have these two types of power poles. And it's really interesting that you have two different types of structures right next to each other, because usually form fits function. And so, they're both about the same height. They're on the same ground, but for whatever reason, somebody decided to do one type of power pole and somebody else decided to do another type of power pole. And so what I want to ask you all is, for the attachment to the ground, which is a fixed support and which is pinned support? So if this is A over here and this is B over here, we're not going to do a pole or anything, but which of those do you think would have to be fixed? And which one do you think would have to be a pin? And think about in terms of we can think about in terms of stability. So if I had a pin support, say that one, the A case right there. If this was a pin support right there, wouldn't it just fall over? Because there's only one attachment point. But if I grabbed it, if I did a fixed support, now it's not going to fall over. So actually A is the fixed support. B is a combination of pins, and that combination of those pins creates a couple moment, and so it doesn't rotate, but it's the combination of all the different of those 4 contact points with the ground that prevents rotation from occurring. While A, the actual support itself, is preventing a moment, not the combination of the 4 supports in that one. Okay, our positive sign convention, we are now going to have 3 equations of equilibrium in 2D, because we're going to say sum of forces in the x is 0, which means that nothing is moving in the x direction. Sum of force in the y, nothing's moving in the y. And then sum of the moments means that nothing is rotating. So we're adding that sum of the moment equation because we need to make sure that nothing is going to rotate as well, because we now have rigid objects. So here's an example where A is a pin, B is a rocker, and we see our FBD. Well, pin is going to have an X and a Y. The rocker is just going to have something perpendicular to the surface that it's connected to, so it ends up being a horizontal force. Notice that all the dimensions are given and all the forces are also labeled with their value right there. So when we look at a pin support or a rocker support, we don't think about the overall stability and how this thing is going to stay in place. We just think about what that particular connection or support is doing. So the pin is an X and a Y. The rocker is just the X force right there. This problem here, we have kind of a typical bridge. We've got a roller at A and a pin over here at B. Notice that they remove the roller. They remove the leaves or flange off of that pin connection there. And they only draw the forces, because remember, we're replacing the physical objects with forces. So don't draw the supports anymore. The supports are gone. That's what we are replacing. Again, notice all the dimensions are on there. All the applied forces are labeled. And also notice that even though there is no horizontal force applied to this thing, we still are going to include a BX. BX, when we start solving for this, we are going to find that BX is equal to 0. There is no horizontal force. We don't need a BX. But if you leave that off, that to me looks like a skateboard. It looks like a roller. So put it on there regardless of what the loads are. Because what if I change the loads and said, oh, well, now I'm going to 15 kips at an angle. Well, now that BX is there. So draw don't start solving them. Draw all the possible forces you could have at that support. Only the correct forces, like this BX, right? Don't leave BX off. Put the BX on there. This one here, another example of how we can use this as the pictures change. We've got a roller and a roller. So what do we see? We see forces perpendicular to that surface. This is a cable up here, so we see a tension in the cable. Now they inclined their axes. X and Y are at an incline, and they show, even though G was given in this problem as going straight down, they broke it up into X, into these inclined X and Y. It's one way I found that's really easy to figure out whether you should incline your axes or not is just count the number of things that you have on the incline relative to the number of things that you have horizontal and vertical. Whichever one has more, then use that axis. So if there's more things that are horizontal and vertical, leave your axes horizontal and vertical. If there's more things that are on the incline, then incline your axes. And then I see a great question here. For hand-drawn FBD, should we try to make the object look like the real thing? Yeah, you can just generalize it as a shape. Absolutely. Don't feel like, you can make this just look like a box there. Okay, let's talk about two force members. Every single hydraulic cylinder on this backhoe is a two-force member. And I have a little example here, a little demo I set up in my garage. And what I did is I have these load cells. And so the load cells are measuring the force in this yardstick up here. And so I'll measure AX there. Then that's the AX and AY applied to that yardstick. And then I'll measure BX over here. And I'm measuring those there. And those are both pin supports. Now, if I put the 5 pounds right here, then I get this AX and AY. I get I get AX around 2, AY around 2. I get BX around 3 and BY around 3. Now something really cool happens when I move that 5 pounds and I put it over here at point A. What that does is this yardstick up here, it only has 2 locations with forces. Okay, that's a 2-force member. So let's write this down. A 2-force member, only 2 locations. Need some more room here. Only 2 locations with forces and no moments. So we didn't talk about moments, but we're gonna. Cannot have any moments. As soon as there's any moments, it's not a 2-force member anymore. Okay, what that means is that the line of action always goes between the 2 points where the forces occur. It doesn't matter how many forces I have at those 2 locations. And let me change it. Instead of 2 points, let's change that to 2 locations. Because that's what we called it before. 2 locations where the forces occur. So it doesn't matter. I could have 1,000,000 forces at this location and 1,000,000 forces at this location. But if there's only 2 locations where forces occur and there's no moments, the line of action goes between those 2 places. And so that's why you see my AY and the BY go to 0. Now I have some error in my actual setup here. So my AY and my BY that I'm actually measuring on the computer screen there in the picture are not 0, but effectively they are 0. So we end up, all the forces go along that. So think back to those hydraulic cylinders. If in those hydraulic cylinders, we can only, if we have all the forces, let me grab a shorter one here. If we only have 2 locations where the forces occur, that means that the forces are either going to be just in pure pushing or pure pulling. Which means that the hydraulic cylinders are not going to do this. This is what happens when we get a moment. and when we have a moment within our system. So that's why all the hydraulic cylinders, we're only going to have two locations where forces occur. If we go back up to that picture of the hydraulic cylinders, look at that. They have, this one has got a pin connection, a pin and a pin. This one right here, a pin and a pin, only two locations, a pin and a pin. So every single hydraulic cylinder that you're going to see is a two-force member. Okay, then we've already written this down. The only thing I want to point out here is that they can be in tension or compression, right? If they're pulling, they're in tension. If they're pushing, they're in compression. The other thing is they do not have to be straight. We could have a rigid object that is curved. And as long as I only have two locations and no moments, then it's still going to go in between. The line of action is going to go in between those 2 points where the forces occur. Okay, so everything else, if it's not a two-force member, basically means it's a multi-force member. And a multi-force member means that there's more than 2 points. So if there are more than two locations, it's a multi-force. Or if there's a couple moment, if an M, it's a multi-force. So I know I'm pretty much out of time, but I just want to say one more thing, and that is, what does that mean for us in statics? What that means for us in statics is it reduces the number of unknowns so we can solve a problem. In this dump truck right here, B to C is a 2FM or a two-force member. And we'll continue talking about this on Friday. It's a two-force member. So even though you look at B and you say, oh, well, that's a pin or a hinge, we are not going to draw that as a BX and a BY. We're going to draw it as an FBC because we know the line of action goes between B and C. We reduce the number of unknowns, so we only have 3 unknowns in that problem and we can solve it. So we have to be able to identify two-force members to be able to solve our problems by reducing the number of unknowns. You all have a great rest of your Wednesday.